Okay, good afternoon and to everyone. And it's been an honor and a privilege to be here as the newly elected fellow and also to give the first speech. So I was thinking about that, what should be my topic. And having taught at the university for a long time, more technical stuff, and I was thinking how I'm going to describe what I've been doing for the last 15 to 20 years. So I thought it's going to be wireless exchange of electrical energy between devices called X2X, and you must be wondering what X2X is, and I'll explain in a minute. So before that, I just want to tell a little bit about myself. I was born in Sri Lanka, and then I came to New Zealand as a Commonwealth doctoral scholar to do a PhD. So I did a PhD on brushless DC motors, and this is my study. As you can see, that's a long time ago. John Boyce was my supervisor, so I was on motor drives. And the name is brushless, short slotless, ironless, sensorless motor. So my fellow students and the friends used to laugh at me saying that it's a useless motor. There's nothing there. But I finished the PhD. This is how we started as a new motor. And it became, this is how I graduated, and a big company. Wellington Drives, you must have heard about that. That's the motor that they further developed. Now it's been sold. So then I went to industry for 2 or 3 years, Fisher and Parker, and I was concentrating on designing this brushless DC motor. You must have seen that in your smart drive. So then I came back to the university as a research fellow. So you must be wondering what my field of research is. So my field of research is power electronics. And if you're wondering what it is, so if you can see that on the left-hand side is the primary energy sources. And you can see hydro, oil, coal, wind, solar, or nuclear. So that's the primary sources of energy, and that's being converted into electricity. In New Zealand, it's about 230 volts, 50 hertz for single-phase supply. So then what you have on the right side is you can see the appliances, the applications there. There are a variety of applications there, from home appliances to industrial automation there. You can see the motor drives there, electric vehicle for an example. So in that form, we can't use it. Somehow or other, we need to convert them. So we need essentially some sort of a conversion. When we do that with electronics, and we call it power electronics. So that's my field of research. That's what I've been doing for a long time. So how fast, how quickly we can change this energy, electrical energy, into a form that we require on the right-hand side. It's called the power. So how can we do that in electronics? So these are the switches that we use and to do that. So what's the motivation for me to do the research? So mainly, I want to solve societal problems there, or industry problems there, with the emphasis on the need and the impact. And I want to be very innovative. I want to have some solutions, particularly improving the performance. In comparison to how efficiently I can convert that, cost, size, reliability, number of things there. So depending on the application. And of course, it has to be sustainable. So my research. So when I came to the university, I was doing a lot of work, development work. So I started a number of projects. So one project is a new generator concept. This was patented at that time. And what it does is to take a very simple induction motor, very cheap, and then can we connect it to a wind turbine so that I can generate electricity. It's a very cheap one, especially in rural applications. And there you can see the turbine is the one that the green part, and it's connected to the rotor in the middle. There you can see that on the rotor that is spinning, and in between is the yellow part there. That's the air gap. That's the rotor has to spin. The outside blue part is called the stator there. So it is spinning that you can generate electricity, so I can supply to the house there. And if it's too much excess of energy, what I can do is I can store in the battery. So I want to go further step. I want to retrieve that energy. Then I was thinking about that. At that time, Professor John Boyce is the pioneering of the wireless power transfer. He was working on one-way wireless power transfer. So I was thinking that air gap is very small. I want to make it bigger for many applications there. Then I want to retrieve energy wirelessly going both ways. So that is how I started the concept. That was quite some time ago. So that was the system that we built at that time for this generator. So this is how that concept came, bidirectional wireless power transfer. So let's have a look at anything to anything. That is to wirelessly exchange electrical energy, X to X. So the concept, in a way, it's not new. And this is the V to G, if you can use the electric vehicle, battery of the electric vehicle to store energy and retrieve energy. So you get it from the grid and put it back into the grid. Now it's been developed now, you can buy all your electric vehicles can do that. You can power your home, building, homes and the loads there, and also the vehicle to vehicle. So this is wired, but I want to do it wirelessly. So there are many other applications, and if you look at them, emerging, energy recovery, phone to phone you can charge, laptop to laptop, robotic applications there, and also the automated guided vehicles in industry, and underwater and sensors. So there are many applications there. So let's have a look at what does it look like. And here's X, this side is X. Now we want to do it, energy exchange. So what we need to do is a bidirectional energy exchange, and that is going back and forth, however you want to. But there are two ways to do that, wired or wireless. Some will do it wireless. So the X can be any number of X's. There are many applications that you can exchange energy wirelessly. So this is how I started. So I'll try to keep it very simple. So let's take an example, electric vehicle, how we charge it. So there you can see in wireless charging, and this is called a near field charging, we use a magnetic field to transfer energy. So this is how it happens. And here is the grid, or the electric energy source, or the X there. Then we have a coil, it's called the charging coil or charging pad, buried or surface on the ground there. Then we have an interface, which is an electronic interface. Car comes and parks. On top of that, underneath the car, there's another coil mounted there. So then what we do is, what we get is low frequency 50 hertz, what you get over here in the mains. We convert that into high frequency. We excite the charging coil, and that creates a pulsating magnetic field. And then this is coupled with the coil that is mounted underneath the vehicle, and through the magnetic coupling, across the air gap, energy transfer takes place. So this is wireless power. So I want to do that going both ways. I can store energy, retrieve energy wirelessly. So this is what I started a long time ago. So here's a typical wireless X2X system. I'll just show you in the conceptual level without any electronics or any technical details. And there you can see, for an example, if it is electric vehicle battery, and the left-hand side is the grid. And these are the two coils I was talking about. And these are separated by an air gap. Then what we do is we use a capacitor. We connect the capacitor either in series or parallel with this coil to negate the effect of that coil, and to improve the power transfer and also make it very efficient. And then what we do is we want to have high frequency, we have an electronic converter, and then we generate a high frequency current. As the current goes through the coil, it generates a magnetic field, and through the magnetic field, we transfer power across the air gap. So this is wireless power transfer. And as you can see that this happens at very high frequency. And then we change it to DC to charge the battery. And the left-hand side again, you can see that low frequency is again converted into high frequency. So this is a typical system. So then we control all these converters. These are electronic converters digitally. So that is what we do. So here is how it looks like. I just put the blocks before. There you can see all these are switches, electronic switches. And this is how it looks like. So we control all these things and to control the power flow. So there are some challenges to overcome. At that time, we didn't know how to do it, but we came across it, how to do it. Now we have advanced technology. And you can see that some of the contributions, not all, and what I have done. And there you can see we have come up with methodologies or theory behind it, how to control the energy flow both ways, and also the amount of energy that can be transferred. And also the synchronization. Why? Two sides are completely decoupled. They're separate. And how do we synchronize them together without any communication? So we have done it. And also different control strategies, how we can make it very efficient. And the variations, all the components, still I can transfer and regulate the power. And we proposed novel circuits, may efficient, cost-effective, and special modeling techniques, how we can model, how we can understand, and how we can aid and the design process and implementation. And the coil design, how we design these coils, and can we use 3D printing, and we looked into that too. And how do we exchange energy among multiple devices and different places, how do we make sure, how do we control it? And also, how we can design and implement from low power to very high power too. So we have done this. So just to give an idea of what we have done, first prototype we built, and I would like to thank Dulipa for that. At the time, he was my boss postdoc, and he helped develop. We didn't know how to do it. We spent a lot of time. We didn't have money, and you can see that the simple systems that we had, these are the coils that you can see, and how we developed this one. And these are subsequent prototypes. There you can see again the coils here, and from different systems, not only one-to-one, there are too many to exchange wirelessly power. And there's another one there. You can see all the inductors and the capacitors, and these are the capacitors you can see. These are resonance circuits. And this is now system. It was a long time ago. And this is the first prototype that we built. And you can see that it's about 400 millimeters air gap. So we demonstrated. I'd like to thank Michael Need, that was my PhD student, and also Dulipa building this. And that was a long time ago. And since then, we have come a long way now. Okay, it's just to show some contributions and modeling. How do you model? Capacitors can be connected parallel, series, and combination of that. We came up with a model, and we can understand whole circuit and for different applications under different operating conditions. That's a prototype. And then the variation of parameters. So if the magnetic field changes, capacitor values or the inductor value changes, we compromise power flow. So what can we do? So we optimize. We can control these converters, whether series or parallel, very efficient. Optimal control, some of my students. And again, how we synchronize both sides. And these are the test system that we built. And new coil designs. It's called topology optimization that we have done it, how to improve the performance of the coil, same amount of magnetic material, cost-effective new coils, and also how we can combine these converters. So you can see on that box there, the red dotted line, two converters. Can we combine them into one? We have done that one too. At that time, we didn't have money. We had used plastic boxes, and that we used that to compromise. Okay, so I go, and this is with the, how we do that with the vehicles are moving, and how we can wirelessly charge, how we can use supercapacitors to absorb that energy and put it back again. So these are some of the contributions, and acknowledgement I want to do it quickly, and the reason is I wouldn't have done any of these things without these people. Especially, I would like to thank all my past and present students. And without their help, I wouldn't have achieved it. And secondly, I would like to thank all my colleagues at the university and who work with me in my power electronics group and my university as well. And then my family back at home. And without their help, I couldn't do that. And also, finally, my family here in New Zealand too. Without their help, I wouldn't have achieved it. Thank you.